Okay, now we're going to look at other solar systems. Um, Basically, answering the question, damn well there are other uh, solar systems. You've seen pictures of them already. But what I want to show you now is uh, that we know a lot more than just whether solar systems are out there. And we know that because of a few search techniques. They come into two categories as indicated here. One is associated with direct detection and then gravitational detection. Um, and basically, uh, a lot of it has to do with the effect that the planet is going to have on the parent star. It's going to cause it to wobble. If they're close enough, then we can take pictures of these guys, which is another method of detection. And then we can also have gravitational microlensing. Most of the observations we see, though, are basically one associated with wobble. Either we see the star move back and forth, or we see a Doppler shift. So we can detect it in either way. And the idea is that the unseen planet is going to cause the wobbling of the star. The star and the planet are really orbiting each other. The example is basically this. Jupiter is running around at 13 kilometers per second. It's a certain distance away from the sun. And the center of mass of the Sun-Jupiter system is just outside of the diameter of the sun. So, this sun wobbles a little bit. The example I'm going to get across to you is the same one as when you used to, as a small child, have one of your parents share a seesaw ride. So you would, if you wanted to have fun, then what your parent would have to do is sit really close to the fulcrum of the teeter-totter, and you would sit far back, and then you could both enjoy the ride and push off and create the motion together. If your parents sat in the seat just as far away from the fulcrum as you were when you were little, there wasn't much fun going on at all for the both of you. But it would be much more fun if you both controlled the contraption together. Well, so that's sort of what's going on with the sun and the planets. They are orbiting around a common center, and for the Jupiter-Sun case, the effect is that Jupiter causes the sun to wobble at a rate of 13 meters per second. And that is something that we can pretty much detect. So if some other creatures were out there, they would look at our sun and detect 13 meters per second, and they would be able to tell that there was a planet Jupiter out there. Okay, current state of the art is about 3 meters per second, and the hope is that with new techniques we can get to much better than that. And to remind you what that means in terms of miles per hour, 65 miles per hour is equivalent to about 30 meters per second. The other way that we can detect star wobble is astrometrically, meaning we can see where the sun lies relative to other stars. Okay, so that wobble for the sun is pretty small, but actually kind of measurable with our technology right now. The first extrasolar planet was observed in 1995. It had a velocity that was, maximum velocity from the Doppler shift was about 50 meters per second. And the period, though, is very, very short. So here it started at 2, and we see it coming back around at about 6. So it had a period of about 4 days. We don't have anything in our solar system that goes around the sun that quickly. It's very, very close to the star. It's half the size of Jupiter, And let me remind you that the size of the sun, its diameter is about 1% that of the distance between the Earth and the sun. So this is, the diameter or the orbit that this Jupiter is going around that star is 5 times more than just the diameter of the sun. So it's really, really close. That's why we call them hot Jupiters. Now, another way that we can detect the stars, or actually planets going around stars, is the method called transit. And what we see here is a blue dot representing a planet, and it's going around the planet like this and going across the disk of the star. And as it crosses the disk, it's going to darken the disk, right, as it's going across. And then out here, the star is completely, illuminated again. There's no blockage of the starlight. So in this period where this planet is moving in, getting close, the star's intensity is constant until the planet gets in front of it, and then it goes down. It takes a while, and this little piece here is an indication of the size of the planet as it's going across. And then as it's going across the star, then it's going to be at a constant, the star is going to be at a constant intensity until the planet leaves. Now, this is the method that we've been using with the Kepler spacecraft, and there's something like on the order of 30,000 planet candidates. So here's a simulation of what we'd expect to have happen for a transit. So here we go, and there's the transit of the guy in front. Now that's sort of what it looks like when we have Venus or Mercury going across the sun. And I was lucky enough a few years ago to see Venus going in front of the sun. I guess most of you are not going to be able to see it in your lifetimes. Anyway, here it goes again, and it's like a little dewdrop going across. Okay, here's some more data. This is a transit that was observed. And this is, a picture of the Kepler spacecraft. As you know, Kepler's got problems. It's lost 2 of 3 momentum wheels, meaning it can't control its position to the accuracy needed for its primary mission anymore. And here's a picture of Fomalhaut, which is a pretty bright star in our southern sky. And this picture shows a planet. I'm not sure how they can determine that these 2 are planets rather than all the other things out here that look like just regular speckle noise to me. Okay, what is the scorecard for exoplanets? Well, it's improving all the time. When I first started this gig, I picked up slides from friends, and they reported that in 2007, now I started teaching astronomy in 2010, so at that time they had 260 planets around 220 stars using these various methods. And then later on, after a year of me following stuff, we're up to about 400. And a couple of years ago, we were up to 700 planetary systems, almost 900 satellites. And basically, I've given up on keeping track of that, and all I do is go to this website and see what the current reading is. So now we're showing 3,500 planets, 2,600 planetary systems, and almost 600 multiple planet systems. So 600 systems that have more than one planet. And these numbers are increasing all the time. I mean, it's like a cottage industry. All right, so in terms of finding exoplanets, the next thing that one could ask is, what about intelligence on those planets? We'll talk more about life in other regions in the solar system, but also on exoplanets and what is that probability. That's our last section of the Astronomy 20 or 25. But as far as extraterrestrial intelligence, it's a fun topic. And you can go and help to determine if there is exoplanets with intelligence on them, and use this website. This is a thing called citizen science. Now, another thing, there's this thing called Tabby Star, which people believe, or some people believe, could be the result of something like a ring world sort of construction around another star system out there. I haven't read this paper, but that is something that one could look at. Now, one of the problems that we have with all these exoplanets is, just as I indicated before with that first chart of the first exoplanet discovered, we had a planet the size of Jupiter that was rotating really, really close to the star, or orbiting very close to the star. And that is one of the standard observations that we see. So if we look at the planetary mass here, and we're looking for massive Jupiter, this is the guys that we're talking about. They are very, very close to the star and very, very massive. We call them hot Jupiters. And the question is why are we detecting all of those all the time? This chart here, as you can see, is from that website that we were just at. And this is a gathering of all the data that we currently have on all the exoplanets and their masses versus the period of the orbit. So we have a lot of these guys that take only a day or so, and they are the mass of Jupiter. And so just like that one that we saw before, and we don't see very many, we see a lot of those, and we see another bunching up here, which is, again, massive planet, size of Jupiter, and it's about 100 days long. And then we have some guys down here which are sort of what you expect for Earth types things. Remind you that the Earth is about 300 times less than that of Jupiter, so that's in about the right order. But we have all these hot Jupiters, and the question is why in the world do we have them? And so that is the next installment. And if you want to, you can. These are some questions that I would give to my face-to-face class. And we've talked about velocity and acceleration before. And the question is basically how long does it take to get to the nearest planet? All right. Our next topic is going to be an understanding of these hot Jupiters in reference to our solar system, and then we will finish up with this section.